Feathers have always been synonymous with birds, but they have also been associated with dinosaurs for a very long time. In 1861, Hermann von Meyer was describing an exceptionally preserved fossil that had been found in limestone near Solnhofen in Germany. It looked very similar to another German fossil described in 1859 of a small dinosaur called Compsognathids, but what was lying in front of Meyer had clear imprints of something unexpected. This was the first time that a link between dinosaurs and birds had been found. Just 2 years after the publication of On the Origin of Species, a dinosaur was found with that most bird-like of traits, feathers. Thomas Henry Huxley began promoting the link between dinosaurs and birds through the 1870s, but it took to the 1970s and the dinosaur renaissance for the idea to truly take hold, with the finding of Deinonychus. Feathers are a very fragile feature, can decay easily, and need special conditions to fossilise. There are places where conditions produce remarkably well-preserved fossils, like at Solnhofen. These fossiliferous gold mines are called Lagerstätten, exceptional preservation locations specifically being Konservatlagerstätten. A rush of exceptionally preserved feathered animals started coming out of the Liaoning province in northeastern China in the late 90s, when developments uncovered several Lagerstätte formations. It wasn't just birds and feathered dinosaurs. Solnhofen had produced fossilised pterosaurs with a strange fluffy covering. These were often overlooked as products of preservation, but as exceptionally preserved pterosaurs were being dug up in China, this view changed. These weren't hairs, they were fibres that some claimed were proto-feathers. When we only have a few exquisitely preserved fossils and some living relatives, how do you make determinations on animals that we do not have the evidence for? Well, you could use phylogenetic bracketing. For this, you need a robust phylogenetic tree with some relatives that you know something about due to fossils or living relatives. Let's take this as an example and have animals A, B and C. If A and C have the same feature, it's probable that their common ancestor had that feature and so B probably had it too. This is the relationship between pterosaurs, non-avian dinosaurs and birds. Pterosaurs had a filamentous covering. If we consider these proto-feathers and modern birds have feathers, their common ancestor probably had some kind of feather, and so non-avian dinosaurs would have them too. But don't expect me to be pulling out images of Triceratops looking like a peacock or a Apatosaurus looking like a turkey just yet. Let's have another example. Let's take African elephants, Mammuthus primigenius, and Asian elephants. Both African and Asian elephants are predominantly hairless. There are other signs that their common ancestor was also hairless, but we know that Mammuthus primigenius was not due to frozen skin and its more common name, the woolly mammoth. Before we take a look into how this might happen, let's take a brief look into how feathers came about. The skin of most animals is dotted with points of protein accumulation and the activation of genetic pathways. This is the starting point of so many skin features, called placodes, in many animals. Odontodes in sharks, squamate scales in reptiles, feathers in birds, and hairs in mammals. All of these are started by FGF, fibroblast growth factor, and then SHH signals, sonic hedgehog. No, seriously, that's what it's called. HH signals produce denticles, so hedgehog, and this variant is called sonic after the researcher saw the game character in a magazine. For both scaled reptiles and birds, this works with cornea's beta proteins and keratin to form scales and feathers. They use the same pathways and the same material to make both. For feathers, birds have 126 extra genes than scaled reptiles, but still have the genes for making scales, and the switch between is surprisingly easy. If you don't believe me, look at the chicken. Chickens have scales covering their lower legs and feet, but with the switching on of a few genes, some breeds of chickens have turned those scales into full-fledged feathers. I know this is a pigeon, but you get my point. One of the key points of phylogenetic bracketing is that it has to be used carefully and only when there is no preservation likely. So we have to look closer at what the fossil record shows and what inferences we can draw. Pterosaurs are important as they can indicate what features primitive dinosaurs might have possessed if they also appear later in the fossil record. In pterosaurs from the Middle Jurassic of China were found monofilaments, tufted monofilaments, bunched fibres, and down feathers. And all this in one pterosaur, an Compsognathids. Another cute pterosaur called Jeholopterus had tufty down-like feathers, and Saurorisians was found with brush-like filaments. So, if we look at this dinosaur and pterosaur phylogenetic tree, we definitely have monofilaments, tufts of filaments, and two types of brush-like filaments. Notably, no pterosaur has been found with scales. Dinosaurs from every major group have been found with scales or scale impressions preserved, so these were probably secondarily lost in pterosaurs. Going up, ornithopods have been found with scales, and there is evidence of monofilaments and tufts of filaments in their lineage. Marginocephalians, the ceratopsians and pachycephalosaurs, predominantly had scales, but there is evidence of monofilaments. The thyreophorans, stegosaurs and ankylosaurs, and sauropods have been found only with scales, not a single filament of a feather. The theropods, though, they have been found with scales, monofilaments, tufts of filaments, brush-like filaments, open pennaceous feathers, and closed pennaceous feathers, in many ways indistinguishable from modern birds. Those last two involve a central rachis, or pen, with filaments branching off. In the closed form, these filaments develop hooklets, which knit the filaments together into the feathers we know today. So it seems that monofilaments existed in the early ancestors of dinosaurs and pterosaurs, being secondarily lost completely in the sauropods and thyreophorans. The same is true of the tufts of filaments, these being lost in the marginocephalians, and even with brush-like filaments, these seem to have existed before the dinosaur-pterosaur split, but lost in the Ornithischian dinosaur line, only being seen in the theropods. The then theropods went even further, evolving the open and closed pennaceous feathers. This gets more complicated when you take a closer look, so let's start with the Ornithischians. The most basal Ornithischian that we have data for is Tianyulong, a 70 cm heterodontosaurid from Jurassic China. It was covered in long monofilaments. These were hollow and bear resemblance in size, shape and material to porcupine quills, although in Tianyulong these were not modified hairs. In more derived Ornithischians, the scales of Scelidosaurus show that the loss of feathers occurred early in the thyreophorans, and all preserved skin of stegosaurs and ankylosaurs have shown scales. On the ceropod end, however, there is the basal neo-Ornithischian called Colindodromeus from the Middle Jurassic. While it had 3 different types of scales, large sections of its body were covered in tufts of filaments similar to downy feathers, sometimes called dinofuzz. The true ornithopods, the iguanodontids, the lambeosaurians and the saurolophines, all had several different types of scales, but not one filament has been found. This is despite there being several ornithopod mummies, some of the best preserved specimens found. In the basal ceratopsian Psittacosaurus, a specimen from China revealed a mass of scales, but also large monofilaments, similar to Tianyulong's. All of the Neoceratopsian skin impressions found have shown nothing but scales, although some recent reconstructions have added monofilament spines because of Psittacosaurus. Linking these to ancestral features is difficult, as feathers could be completely lost and then re-emerge down the line as turning on those genetic pathways becomes advantageous again. It's a complicated topic, and it's about to get more complicated when looking at the Saurorisians. All we have is that sauropods were all scaled, so we're going to go straight to the theropods. Starting with the most basal that we have evidence for is the ceratosaurs. Here we only have skin impressions of scales. A bit further up we have Saurorisians from the Upper Jurassic of Germany. There are indications of a coat of fine monofilaments, almost like a covering of hair. The unfused bones indicate that this was a very young individual. It's possible that theropods of this type had a filament covering, but lost it as they aged. Further along we have the Allosaurids, all scaled as far as we know. Same with the Carcharodontosaurs, all scaly. Next we get into the Tyrannosauroids, and we have passed monofilaments and dived straight into downy tufts of filaments. There are numerous examples of these tufts: Guanlong, Dilong, Eotyrannus, Zhongguanlong, and the largest, Eutyrannus. This does not mean that they were all fluffy. Numerous skin impressions of various parts of North American tyrannosaurs show that they were scaly, at least the adults were. It seems some of the Asian and European tyrannosaurs were using fluff to insulate themselves against the colder climate, and the large American tyrannosaurs had lost their feathers in the hotter climate of North America, adapting as the Asian elephants and mammoths would do over 60 million years later. Further along were the Compsognathids. It seems that all of this group had monofilament feathers, the most obvious of these being Sinosauropteryx. Melanosomes, parts of cells responsible for feather colouring, were found preserved in Sinosauropteryx filaments. If the melanosome shapes are consistent with modern birds, it allows us to reconstruct Sinosauropteryx's colouring. There's been playing around with monofilaments and tufts, but next we get into the really feathered dinosaurs, the Maniraptor. First we have the Ornithomimosaurs, the ostrich-mimic dinosaurs. These seem to have had open pennaceous feathers. These had a central rachis and tufty filaments, very similar to modern ostriches, making the name even more fitting. The later Allosaurids showed a turnaround as they seem to have gone back to almost microscopic monofilaments. Despite the incredibly long legs and bird-like features leading some in the 90s describing them as the first flightless birds, these would have looked less like modern flightless birds than the Ornithomimosaurs. Up next we have some of the weirdest theropods, the Therizinosaurs. These had turned herbivorous, with pot bellies, long necks and massive claws. One of the oldest shows signs of brush-like filaments, the most advanced form of pterosaur feather. It's widely accepted that all other Therizinosaurs had at least this level of feathering. With the Oviraptorosaurs, we get the first signs of what we would today call feathers, a long pennaceous feather with a closed vein. These, though, were symmetrical, incapable of forming an aerofoil. It's widely believed that these large feathers were mainly adapted for display, the largest occurring in the arms and tail. But if you thought Therizinosaurs were weird, the feathered Scansoriopterigids give them a run for their money. These had long pennaceous feathers on the back and tail, but little tufts around the hands and arms. They focused on developing large membranes supported by an extra bone that grew from the hand. This was no modified finger, but a whole new bone found only in this group of dinosaurs. Although they could not fly, they seemed to be like flying squirrels, gliding between trees. This particular animal is called Yi-Chi. That's its generic and specific name. Unsurprisingly, this is the shortest dinosaur name, and the shortest binomial name allowed by the International Code on Zoological Nomenclature, tied with the Great Evening Bat, Ia-Io. The Troodontids and Dromaeosaurids, both having closed pennaceous feathers, were similar in many ways. Both have evidence showing full feathers on their arms and tails. The Troodontids and Eudromaeosaurids, like Velociraptor and Deinonychus, probably use their feathers for display, insulation, and even in predation strategies. But the Microraptors of the Dromaeosaurids were doing something different. Dinosaurs like Microraptor and Sinornithosaurus had developed asymmetrical feathers, flight feathers. They did not have the ability to fly, but could use their arms as a light aerofoil to glide between trees. Microraptor went further with flight feathers on its legs. Not great for walking, but it could glide a lot further. Analysis of melanosomes in Microraptor feathers indicate by their shape and layering that this dinosaur might also have had iridescent feathers. But this branch is not where modern birds came from. As we get closer to birds, things get a bit hazy. There is the group Anchiornithid, but some class these as being part of the Troodontids. These dinosaurs looked very much like small flightless birds. They all possessed pennaceous feathers, they were symmetrical so could not be used for flight, and most of their bodies were covered with open and tufty feathers. Finally we get to the birds, the aves and the aviolans. Asymmetrical flight feathers on the arms and capable of powered flight. Recent studies have started placing the basal member of this group as Archaeopteryx. It was a weak burst flyer, but established how later birds would travel through the air. Dinosaurs developed gliding at least 3 times: Scansoriopterigids, Microraptors, and aviolans. The Scansoriopterigids show that this was not a consequence of closed feathers. Small, light-boned animals with a high metabolism and efficient breathing system provided a good base for a flyer. An arboreal lifestyle in the trees also made gliding and flying advantageous. The Scansoriopterigids seem to not have been that successful, not lasting into the Cretaceous. Frankly, feathers are a more resistant, efficient, and repairable aerofoil than skin. The feathered gliders seem to have won out. Both gliders and flyers lasted up to the end Cretaceous mass extinction and the end of the non-avian dinosaurs. Both groups took hits, but it was the flyers that made it through, the Microraptors going the same way as the Pterosaurs. By the end of the Mesozoic, the Pterosaurs had been masters of the skies for over 160 million years, and grew to the largest animals ever to take to the wing. The birds seemed poised to take this place as soon as they were out of the picture, ready to spread their feathered wings and join the mammals on land in taking over these new spaces. Thank you very much for watching. I try to make sure these shorter videos don't take so long to produce, but this one kinda got away from me. I do hope that you enjoyed it, learned something, and I'll be able to refer to it in later videos. Feathers are a fascinating field of study in paleontology right now, and things are moving quickly. This is the most complete and concise information that I have available at the time of production, although updates will almost certainly need to be made. Remember to like, subscribe, ring the bell to be notified of new videos, and share with anyone who might have an interest. I would like to thank my patrons, Arachobia, my first patron, and a special shout out to Dracano, my first genus level patron. If you would like to join and get these videos a week early, you can click on the link below. Genus level patrons will also be getting the history of Camarasaurus for free as soon as it's edited. See you next time.